Magnetic levitation technology is an interesting new technology that has many applications in propulsion and mass transportation. A chamber or tube is propelled by the magnetic force generated by opposite forces repelling each other. This process has the advantage of working without friction, which will result in a vast increase of space and efficiency. In fact, one of the key advantages of using a maglev train is that it is able to reach high speeds without the use of wheels or tracks, which reduces friction and wear and tear on the system. Additionally, maglev trains are able to travel at high speeds without causing significant noise pollution, making them more environmentally friendly than traditional trains. However, there are some challenges in building a maglev train. One of the biggest challenges is the cost of building the infrastructure necessary to support the system. The cost of building the necessary tracks and power supply can be very high. Additionally, maglev trains require a significant amount of energy to operate, which can be costly.
Our project consists of wound circular copper wire and a battery with state-of-the-art neodymium magnets connected to either end. In theory, when you put the battery and magnets inside the wire tube, both magnet ends should connect to the wire and complete the circuit of the battery, inducting a magnetic field inside the wire and pushing the magnet. This process repeats every time the magnets both connect, propelling the magnets forward. In other words, we are basically short-circuiting the battery to give us the electrical energy it needs to propel itself forward. For this to work, you would need your magnets to have a larger diameter than your battery, and for the diameter of the tube to be the greatest for it to fit through. The train we are designing operates on the principles of electrodynamic suspension. In electrodynamic suspension, the train levitates above the track using the interaction between the magnets on the train and the current flowing through the conductors on the track. The magnets on the train are neodymium magnets, which generate a strong magnetic field. The current flowing through the conductors on the track generates an opposing magnetic field, which interacts with the magnetic field of the magnets on the train. This interaction causes the train to levitate above the tracks and propel the battery forward.
The principle for the propulsion of the train uses the Lorentz force. The Lorentz force is the force exerted on a current-carrying conductor placed in a magnetic field. It is the interaction of the magnetic field and the current that induces the force that propels the train forward. It is represented by the formula F is equal to Q times E plus V times B. In this formula, F represents the magnetic force, Q represents the electric charge, E represents the external electric field, which is the electric field of the surrounding environment, V is velocity, and B is the magnetic field caused by the magnets in the coil. We already know how to calculate B for movement in a solenoid. The magnetic field strength can be calculated using the magnetic field calculation for a solenoid, as the battery will create a current. The formula we can use is B is equal to mu 0 and L, where mu 0 is the permeability of free space constant of 4 pi times 10 to the minus 7, N is the number of loops per meter, and I is the current of the circuit created between the battery and the magnets in the wire tube. While we can't exactly calculate all of the values of the Lorentz equation, we can infer the rough positive or negative values of each variable. E, which is the external electric field, will be negligible, but still existing in our calculations. Q, the charge of the battery and magnet train, will be positive, but we cannot determine its exact value. V, at least at the start of the track, will be an extremely small but positive amount as we must push the train into the tube to start the experiment. B is calculatable. If we calculated the number of loops and length of the wire tube, we'd be able to find an average N. And L is the current generated from the battery, which can be found with research by using an ammeter, a device used to measure amps in a circuit. Now we'll draw a diagram to explain this. The train, consisting of the conventional magnets, the battery, and the copper wire, will be located in the center of our solenoid. The track is made out of bare copper wire for conduction, and the power supply providing the energy needed to power the train's propulsion system is the voltage of the battery itself. The train is propelled along the track using the interaction between magnets on the train and the current flowing through the conductors on the track. The current flowing through the conductors on the track generates an opposite magnetic field, which interacts with the magnetic field of the magnets on the train. The propulsion is done by the Lorentz force generated by the interaction between the magnetic field and the current flowing through the conductors on the track. The power supply is responsible for providing the energy needed to power the train's propulsion system.
The train is propelled forward using the Lorentz force, generated by the interaction between the magnetic field and the current flowing through the conductors on the track. The power supply provides the energy needed to create the magnetic fields and to power the train's propulsion system.
And now we will see this in action. It took a lot of engineering. You may have saw us in class struggling to figure things out. We looked at the theory and we tried everything. We changed the copper, the battery, the magnets, and the diameter of the solenoid. We eventually had to wind up a coil for the third and final time, but finally we managed to get it working a little bit, and then we managed to create a track. I got it working on curves, and even on a ramp.
In conclusion, this project was an interesting engineering challenge. We wanted to build a magnetic propulsion device to see how maglev trains work in the real world and to gain a better understanding of the incoming technology of the future. It took a lot of troubleshooting to get it working, as we weren't using state-of-the-art equipment, but eventually we were able to see successful and very interesting results. Overall, we learned a lot about magnets and circuitry, and from now on, whenever we see a maglev train, we know how it will work.